Hello, everyone. Okay, hopefully this is working and people can see me. I see we have a few viewers right now, which is good. I'm Jose, and we've got a few talks for you about how Haskell and AI can work together, and some are tool descriptions, some are experience reports. So it'll be a good mix of how people are navigating this new landscape we find ourselves in. So the first speaker we have today is Alfredo. And let me put the description of his talk in the chat here. Why not? Let me copy that over and get you all started. Oh, it's going to be just the title. All right, here we go. Here's Alfredo's title. Okay, and talk will be about somewhere between 20 and 30 minutes, and we'll have time for some questions at the end via the chat. Unfortunately, because of the format, it's gonna be difficult to be interactive. But if you ask questions in the chat, and I think it's really worthwhile, I can pass them on to Alfredo. But for the most part, let's keep the questions to the end. So without any further ado, our first speaker, Alfredo, is gonna take the stage now. So let me set that up. Here we go, Alfredo.
Hello, folks. I hope you can hear me fine. Great. Let me see if I can make this full screen. Great. Okay. So thanks for having me. Today, I'm Alfredo. First of all, sorry for the mess in my room. I'm doing some, renovation. I'm a Haskell senior consultant for Well-Typed, and today I'm going to talk to you about consulting for clients who use AI. Before we start, a very important disclaimer. I know this is a very divisive topic, it's also controversial, and I'm not here to sell you anything. This is not a talk like pro AI, it's not a talk against generative AI. It's merely my own experience report, so you can essentially decide what you can take out of it. All opinions are my own. Well-Typed as a company doesn't have yet a policy about AI. Of course, we can use AI for clients which encourage or require us to do so. And we also offer free cloud accounts for our colleagues of our company to experiment with. But that's as much as we go. With that out of the way, I would like to start with this Venn diagram, which is about us as programmer, and it sort of regards our profession. As an individual, we can essentially do whatever we want with our free time. As hobbyists, we can have total freedom, our code, our time, our tools. So we can use everything we want, processes, workflows, including large language models, of course. However, as an employee of a company, we have to subscribe to the company standards, which can be things like, I don't know, use some blessed build tool or use a particular workflow or, I don't know, a chat client to talk to your colleague, whatever. So you have to give away a slice of the cake, but there is still an overlap, right? However, as a consultant, there is a third layer of constraint here. So you have to also abide to the client processes, which again can be simple things like sorting your imports or, I don't know, indent the code with 4 spaces. So once again, there is an overlap, but it's getting thinner and thinner. So it's interesting to think, where does AI fit, right? And this is my own experience report where I've tried to collapse everything into two realms, the recreational realm and the professional one. And the two circles are still overlapping because I've tried to retrofit some of the lessons that I've learned during the recreational endeavors into the professional aspect. So the professional aspect is, I hope, obvious, right? So we have client projects and we want to balance productivity versus correctness. And it's important here to clarify for the rest of the talk, everything I'm going to say here is under the umbrella of I have, or I'm sort of encouraged to use AI. I'm encouraged, the client is paying for, I don't know, a Claude team seat. So it's spending money. So you have to sort of have a, in a sense, a moral obligation. So take this as a grain of salt when I'm introducing some concept. So there is this sort of balancing act from one side. On the other side, as the recreational, I'm going to briefly mention my experience with Rasholm, which is this toy Haskell compiler that I wrote, written via heavy use of LLMs. And then let's start then. So let's talk a little bit about Rasholm and what I have learned. It's essentially a toy Haskell compiler that you can check. It was written roughly in 1 month as a challenge to learn a little bit about AI in general. As a challenge also because within Well-Typed, once a week we have an internal company talk about projects, and it was my scheduled turn, so I wanted to present something. I said, well, can I even write a compiler that works end-to-end in roughly 1 month? And so I did. It's still under active development to some extent. It now supports most of the Haskell 2010 syntax. It has some basic class auto-deriving. If you define your Haskell data type, you can say deriving, show, EQ, or the usual suspects, and it will generate dictionaries under the hood. It's also interesting because it adds a twist. It's not like a blatant copy of GHC. I replaced the final stage of the compilation pipeline, so there is no STG, there is no C++ emitted, but there is green instead, which is this the acronym of graph reduction intermediate notation, which is an intermediate representation which where allocations are explicit, and as a result, it taps into all sorts of interesting optimization that you can perform. And it also maps very well to LLVM bytecode. So that's what we emit in terms of eventually we'll go from the bytecode to machine code. And as a result, we also support WASM natively. So it's like not a trivial project. I think it was a good candidate for this kind of experiment. There, what worked and what didn't? Well, there, what I tried the approach I tried to take was the approach of a domain expert trying to act as an architect. Over the years, I've contributed to GHC professionally within the company. I'm not like the foremost expert as my other colleagues, but I know how the different stages of the pipeline work. So I was able to sort of retrofit my domain expertise into Claude by writing a design document, which I then incorporated into this Claude.md that if you never use this kind of tool, it's a markdown file that you can write to essentially instruct your AI harness of choice, whether it be Claude or OpenCode, whatever, how your project essentially work. And there, the domain knowledge and this sort of rigid framework about how to do things in a divided et impera fashion really kept the AI on the rails. And at the end of the month, I had something working quite nice. For a demo, it worked quite well. Well, what didn't? It was, as you can imagine, lots of code generated in a very short amount of time. So there was no room for deep understanding. And, I learned a lot about AI tools, but virtually zero about the Zig, which was half the point of the exercise. And the code quality, although I asked Claude to make it as self-documenting as possible. It's probably not the best, but the irony is that I can judge because I should probably learn Zig first. So a bit of a mixed bag here. However, I have distilled working with Rasholm a simple workflow, which I sort of call this sort of two hats approach. I realized that I was wearing two hats when I was working on Rasholm. A architect hat, which was about carefully designing, speccing, and reviewing everything, and then offloading the implementation to AI. If this is a tree, you decompose everything into little sizable chunks, a problem which is sort of a well-defined scope, and then you ask AI to tackle that very precise scope. There is no room for AI to wiggle, right? But then also you need a coder hat when AI sort of drift away or starts goose chasing, where you essentially take the front seat of the cockpit of this airplane that you're driving, you write the code, you own the integration, and essentially now the AI is your sparring partner, is your coding buddy. You can ask AI questions like, what's this library I should be using in Zig to do X? Or maybe you can ask, can you tell me what's the implementation for merge sort? If you think, Copilot or this kind of tools that, predates Claude work a little bit in this direction, right? So you write the code, but sometimes you ingest something that, AI has produced. However, here, on the professional side, there is a bit of tension, right? Because we have different forces at play. The client wants essentially a working system. It doesn't want the system to crumble on a Friday afternoon deploy. It wants fast turnaround, ideally, and max throughput. Essentially, cynically, you might think that the client wants to maximize the value it can get out of you per dollar that he pay for the hourly base rate, where the definition of value here is opaque. It can mean lots of things, but ideally it wants to go in that direction. Well typed, on the other hand, wants correct, reviewable, and maintainable code. I hope I'm speaking to an audience where we all share this kind of vision on software design, especially when it comes to Haskell. What I want as an individual, well, I want deep understanding. I want to understand what I'm doing. I want a career development intended as I do not want to get stuck in a rut, completely giving away all sort of creative thinking, but I also want ownership. I want to be able to explain what this code is doing and why it works the way it does. So these three things, again, in the context of clients who use AI, are in tension, in competition. However, it will be a competitive disadvantage not to use the most productive tools available. And as a good friend of mine would put it, it would almost be immoral not to use this kind of tools, right? These days. So what we do? Well, let's talk a little bit about the professional side more specifically, right? So what worked really well, I think, using AI in general, was the low cost of being wrong, like the baseline says. Typically, when you're working on something, right, you want to experiment on some feature that you're building, right? And you want to come up with a prototype to test your idea, to make sure that this idea, that this feature even makes sense. And typically what you will do, you will build your prototype the same way. I mean, regardless of this is AI or human driven, you will write your prototype by cutting all the corners that you can, just to make sure that the approach is sound. I mean, the architecture is sound, right? And then AI here works really well because you can really speed up the process and you can answer the question, does this even make sense, right? And for non-greenfield things where you have like a code base, also sweeping refactorings are also very good to test design. Mind, we are not talking about refactorings that you do, in a hurry and then you ship. But again, refactorings that wants to test that the refactoring has the expected outcome. I can raise my hand that at least once I have done some refactoring, and then at the end of the process, I realized that maybe the payoff wasn't that great, and maybe I spent a couple of days, a couple of hours, whatever, on client money, and just to realize it was a good lesson, but still of not much good value for the client. So here, again, it's very good, the AI in this context. Another area that really surprised me were bash scripts, right? Because I think, at least to me, bash scripts are really easy to read, to audit for what they are doing, if there are no hidden RM, RF anywhere. But they are actually very hard to write because I never remember the syntax for bash script. So for writing this kind of throwaway scripts, it will actually work really well because, as you can imagine, AI has been trained on a lot and lots of bash, so it was actually quite high accuracy and fast payoff. So that aspect, I think, really worked well. Another less obvious aspect, which also surprised me, it wasn't obvious at the beginning, was AI as a brainstorming partner. It goes a little bit back to the coder hat I introduced a few slides ago. Consulting, at least for us, is a solo work. As a company, we are not a very big company, so typically we get assigned to projects. It's either one of us as a solo effort, or maybe two of us. Really rarely it's more than two people. And as such, it's very hard to bounce ideas off because you don't have any teammate to do so. And okay, I'm just looking at the screen. And as such, this echo chamber might lead to tunnel vision. And the other danger here is to discover the design flows much later in the process, right? So you work on something for a couple of days, whatever, then you discover this thing, the architecture that you built has flaws, but you didn't notice because you couldn't ask your colleague, do you think this makes sense? And in this sense, the AI fits a nice niche. The indirection of explaining the design out loud sometimes catches more bug than the AI reply in a classic rubber duck fashion. But sometimes AI can find holes in the design that you didn't think of. I mean, I have to give this credit. So it's, in a sense, it's a rubber duck that occasionally pushes back. And the nice side effect of all of this is that you throw away higher quality prototype. If you read the Mythical Man Month, there is a nice quote that says, plan to throw one away, you will anyhow. One here means your architecture. So you typically work on some prototype, some architecture, but typically the very first iteration is not that great. So you have to be prepared to throw it away and rebuild another one with the lesson learned from the first iteration. And here, if you do so by throwing away a higher quality prototype, then your time to market is reduced. So that worked really well, I think. But that inevitably introduces a paradigm shift, right? So now here we are going from a developer to an architect. And here I'm naming things differently. So I'm not calling this coder because I want to make clear this has nothing to do with the hats I have introduced. Here I'm purely talking as your professional persona, right? So from a developer, which types code, you end up being an architect, which is now reading diffs. You go from prolonged, sessions where you can zone out and enter the flow into a scenario where you have to do rapid context switch while your AI sessions are going in parallel, and you have to really focus and do your sort of narrow burst of attention. Then you go from I built this to I directed this, because of course you are architecting, you are not building or not as before. And then you go from owning the craft to owning the design, which is actually quite interesting, and it's more profound that this sentence suggests. So we will get back to that. And so the hard part here is not the tooling, is the mental model, because wearing the architect hat is not something that is for everybody. We sign up. I mean, typically when we apply for a job, we know a priori what we are going to work on. I mean, if we apply as a backend software engineer, we expect to do just coding, or maybe coding with something else on the side, maybe a bit of DevOps. But the point being that here there's almost a new skill set that has to be mastered. You are not just a normal coder developer anymore, right? You have to adapt, and you become also a bit of an architect. And not everybody is necessarily ready to do this transition or like to do this transition, right? Because they didn't sign up for. So it's a hybrid model in a sense. It's not either or anymore. It's more an and, right? And this is interesting, I think. Then let's wrap up this section by talking a little bit about the architect role, right? This transition that we go from developer to architect. How does it look like? I watched the talk. I don't remember now the source, but I was watching a presentation, and somebody said, if you are waiting on a single cloud, you are doing it wrong. meaning that now in this agentic era where we can have a lots of different sub-agents running on your process, your AI harness in your cloud terminal, then just sitting passively in front of the screen waiting for a single cloud feels a waste of productivity, feels like a waste of brain cycles. So really what happened is that typically as an architect, you have your Tmax window or your tiling manager of choice with different AI sessions open, maybe for different projects, or maybe for the same project for different Git work tree. So you can work on two different feature branches in parallel on the same code base. And then you have to keep tabs on all of them. If an agent get like a roadblock, you have to unblock it by saying, no, you should do this or that, and then switch tab to another one. So the productive time is actually the sum of the agents that you have running. So now the cost is that you might have to context switch like a manager. And that's, again, pretty aggressive in terms of your brain when you have to switch like that. But some days, unfortunately, that's the entire job. And as a direct consequence of all this churning, right, the architect hat produces a lot of code. So now reviewing code becomes the bottleneck. And I know most of you are involved in open source projects, and you have noticed now the swarm of new contributions, some of which are driven by generative AI. This puts a genuine bottleneck, right? Because typically we like humans to do reviewing before the thing gets merged, right? So what we do for this client, at least, we have a second pass of AI, which aim here is not to replace the human. I want to make clear. It's just to basically catch any oversight, like act as an initial sort of funnel for things which are glaring omissions or glaring bugs. And again, the goal here is to make a tighter feedback loop to not waste sort of idle time, so to speak. For example, for this client, it's me and another colleague of mine which are working on this. And this other colleague is also very busy. His reviewing time is very precious. And typically our review cycles are a bit washed out by this kind of how busy he is. But having actually a CI job that does the first pass, it really helps that his time is now sharp focused on only the obvious problems, where the simple problems have been sort of get out of existence. So that's a tight feedback loop. Of course, this is useful as a first filter, but not as a substitute, because if you offload reviewing to an AI, that sort of dulls your own review muscles. Okay, so the picture I'm showing you now, it almost looks like too happy, right? I mean, there is high productivity, the client is happy. Is this the end of the story? Is this the end of the presentation? I would say no, because I think I'm generally convinced that there is no such a thing like a free lunch in computer science. So I think this thing is no exception. And the risk of long-term exposure, we are not talking about a few weeks here, we are talking like long-term exposure. The price you pay is actually cognitive atrophy, where cognitive atrophy is a term from the neuroscience, which has to do with the plasticity of your brain. It basically means that the brain strengthens the neural pathways that are exercised and weakens those that are not. It's essentially the science behind the motivational slogan, if you don't use it, you lose it, right? This is pretty much the same thing. And this begs the question. I want to make this a provocative question now. Who wrote the code? Us, Claude, a bit of both. And I would like to start this section by introducing a very nice essay that I came across while I was researching material for this talk, which is called Programming as Theory Building, which was written in 1985 by Peter Nauer, which is surprisingly modern. I mean, it did age very well, I think, in modern times. And what Nauer says is that, a program is not just source text. A program is actually a theory held in the programmer's mind, which is constructed by the act of building. And it's essentially the underpinning design pillars which sort of govern the entire source code and explain why things are written the way they are. In that essay, he set the scene by introducing two groups of programmers, Group A and Group B. Group A essentially was sort of appointed to write a compiler for a language L, and so they did. Then the Group B stepped in to write another compiler for an extension of the language by essentially taking all the documentation, all the source code, or if you want, the SDK, but crucially, none of the team members of the Group A. So essentially, what worked there is that this is of course like a fictional thing that Nawar says in the essay, but he sort of theorized that now Group B, patch after patch, ended up butchering the original compiler because they didn't have the theory of what was the reason, like the overarching principles around that code base, and they say they end up eroding piece by piece all the thing. And the documentation here didn't help them because the theory, according to Nawar, is deeply bound to human beings, and the documentation is just a snapshot of a particular permutation of the code. So crucially, what he says is that the program whose theory holder is gone is dead in the water, even if it still runs. And this is interesting, right? Because AI written code is born this way. When we write something using Claude or another model of choice, the model generates the code but holds no theory. It has no continuity. And you might say, well, okay, but that's fine, right? We can ask just Claude to explain the code. So problem solved, right? Well, not quite, because even when we ask an LLM about some code, it works backwards by reconstruction, not recalling, which are very distinct skills here, which are coming into play. Now, luckily, if we wear both hats, either the architect or the coder, our theory is still, secure. We still hold the theory because, in a sense, it's almost as if we are the Group A of programmer. We never left. We are just sort of sitting on the side. So we still hold the theory because we had to generate the design or part of the implementation. However, the more you offload to an AI, the more implementation fluency erodes. By implementation fluency here, I mean really in the literal sense of the term, your proficiency with writing Haskell. I don't know, if you sort of write manually how you do a binary search tree, a binary search on a tree, and then you keep asking Claude to do that for you, eventually you're going to forget, how to do that, or it will be not, just straight out of you. It will be more clunky to recall that. And in a normal setting, the architect role will be temporary, right? So you would return to coding, possibly on a different project, switching hats and sort of reactivating those neural pathways almost immediately. However, and here's the trick, the AI makes it possible and tempting to stay in the architect hat indefinitely. There is no strong incentive for you to get out of the architect hat. And we talked, now our essay is called Programming as Theory Building. And building here is really the key that links everything together. It links, our recall, but also our fluency, but also the ownership, right? So when we write code, at least from my experience, when we write code written by a large language model, it doesn't feel mine, even though I sort of crafted very carefully how to do that. Even if I go into the details of the low-level implementation, the end result doesn't feel as if it was mine. And this is explained in sort of neuroscience very well. From these three papers are really interesting when I read them. And there are the generation effect, the IKEA effect, and the psychological ownership. The first one, essentially, it says that we remember and understand self-generated material far better than the material that we just read. And this, they did like a field study where they separated people in two groups. The first group, they asked to come up with some words and then to recall those words. The other group had to just recall some words which were sort of pre-generated for them. And they noticed that people from the first group tended to score better because they were exercising recall by the mere act of self-generation. The IKEA effect instead says merely the IKEA is a classic reference to what you think it is. The effort that we put into building something makes us appreciate in value much more, things that way. So it makes us feel attached to them. Last but not least, the psychological ownership from peers says that we, come to feel that we own the things we have invested effort, attention, and identity. And this is really interesting, I think, in the context of AI, right? So on a positive note, which wasn't obvious to me until recently, as an architect, actually, the IKEA effect doesn't fire so violently because we came up with the design, but not the implementation. So I worked in the past on teams where historically people are quite some folks are quite attached to the implementation, the code, and it's typically a source of fight when they want to rewrite. Somebody else wants to rewrite a part of the code. I know my precious abstraction. However, here it's much less of a fight because the design doesn't change. You just change the implementation, which is in a sense like a commodity, right? It's something that's been generated, not by you. However, as an architect, I personally struggle, as I said in the beginning, with the psychological ownership. It simply doesn't feel like mine. And with both hats, though, some part of the generation. Yes, Jose?
Oh, no, just the time, we're
I have a time,
30
minutes. Yeah, and it's I'm on okay, yes, sure. Thank you.
You're good, yeah.
Yes. However, with both hats, some part of the generation has been delegated to an LLM, right? So this is important because when we offload any part of the development process to an AI, as an architect, you think deeply, but you don't generate code. When you review code, whether it's human written or AI written, that is reading, is not generating. So the recall effect doesn't fire. And not generating affects our recall and our fluency. And that's what I call atrophy. And now that's the most dangerous part. If you want to take anything away from this talk, you can sort of snapshot this slide. The more atrophy kicks in, and the harder it gets to remove the architect hat, because less fluency means that you're a bit clunky. But then, the client here is expecting you to be super productive because you set the bar so high because now you are using AI. So surely you must be super productive, right? So you have to make up for the lack of productivity to basically to put more time into the with the architect hat. You have to regain the full productivity via that. And the more architect time means even less generation in a vicious circle. So this goes on and on and on. So this begs the question, do we need another hat, right? And before we answer that, I want to present one last study they did from a paper from 2025 called Cyborgs, Centaurs, and Self-Automators, where they essentially divided the more than 200 people into, well, they gave them a GPT-4 AI harness, and they asked to solve some business problem. And they observed people sort of naturally distributed in three disjointed ways of working, three disjointed sort of groups. One they called the cyborg, which is what maps almost one-to-one to our architect, which is basically this so-called fused co-creation. So folks actively collaborated with an AI to get to the final solution, and that sort of improved their AI knowledge, so the new skill here. As a centaur, what they had sort of direct co-creation, meaning that which is basically maps to our coder. They essentially sort of used AI alongside as a sort of sparring partner, as we have seen. So they actually gained domain knowledge just by doing that. The last one is what is so-called abdicated sort of creation, where they completely gave away sort of brain control. They completely put the automatic pilot, and they essentially did, everything was delegated to an AI. And the skill outcome there was they had no skilling, right? And it's interesting how the coder got the right answer most often. And here, the self-automator is the ultimate danger, is where atrophy really kicks in, right? But we have no hat that defends against it. So I think the solution here, which might sound completely anti-climatic, is the third hat is actually a no hat. Put the hat in the closet and work without any AI assistance, as in the quote-unquote old times. But why we need that, right? I mean, as an architect, the architect is actually the most productive, is what works best for a client. It sort of maximize the amount of throughput that is getting out of your hourly rate. As a coder here, you get the best trade-off, but no strong incentive to stay in it, right? Because you have client pressure, you have deadlines, you have everything. The no hat here is that the fail-safe that keep us honest is the only place where fluency, ownership, and recall all fire at the same time. In other terms, the architect optimizes for productivity and throughput. The coder optimizes for quality and correctness, and I will get back to that in a second. I will anticipate a question. The no hat is what optimizes for cognitive preservation. And you might ask, well, surely why the coder now optimizes for quality and correctness? I mean, surely as humans, wearing the no hat, we should be able to produce code which is better than AI assisted, right? And that's a fair critique, but remember the umbrella. We are working under the constraint and under the tension of, a client that wants us to use the AI. So I think the best we can do is to work as a coder if we want to optimize for quality and correctness, but we need to be aware of the cognitive atrophy. So this is the tension that I presented in the initial slide, where we have, as a client, I want fast turnaround, max throughput. The architect hat gives you that and optimizes for productivity. As an employer, I want correct, reviewable, and maintainable code. That's our coder and optimizes for quality. And finally, as an individual, I want the no hat because it's the one that gives me the cognitive preservation. And so here, I'm wrapping up now. I'm basically done. I'm trying to put visually what I've been discussing, where the three hats here are sort of all scoring differently in this radar chart. And you can see quite visually the cost of atrophy, right? The atrophy is, we get atrophy in ownership, we get atrophy in recall and procedural fluency if we don't wear the no hat. And of course, I mean, we can debate on the scores being, lower on or higher than you expect, but these are my subjective rating anyway, so we can chat about those. In conclusion, and I'm wrapping up, reserve no AI time for things that you want to remember in 5 years. Treat AI output as a diff to review, not code to trust. The architect hat is exhausting because you have to do lots of context switches, so budget them wisely. And finally, choose the hat that fits the cognitive job and not the deadline. Here are some references. I can give you the slides after the talk. I'm happy to take questions, but let me briefly close the door because otherwise it's noisy in here with the kids.
Well, thank you, Alfredo. And yeah, if in the chat you want to ask, we probably have time for 1 or 2 questions. I'm going to get Gautier set up here. So we'll add Gautier to stage and swap out these slides. But yeah, thank you again. We get a lot of hot takes when it comes to AI. And so I really appreciate your nuanced view on these things. So thank you for that. And I think it was a great start for discussions. Let's see if any questions came up. Okay. Oh, there's also that slight delay, so we'll give another minute. And while we're waiting to see if a question comes in, our next speaker is Gautier Di Folco, and he's going to be talking about LLMs as an SDL support. So it looks like we had no questions. Thank you again, Alfredo. And
thanks for having me, folks.
Yeah, of course. And thank you for the talk. And Gautier, take it away.
Thank you. Hello, everyone. Thanks for attending to my talk. I will present you my current usage of LLMs as a support for day-to-day job as a software engineer. So briefly about me, I'm basically a software engineer because and currently I'm working as a backend developer at Wire. I'm also I do a lot of first contribution, and currently I'm in the Haskell security response team members. So we are dealing with all the at least with most of the security issue we can get in the Haskell ecosystem. A few words about Wire. Wire is a German company which is delivering communication tool for big and smaller companies and for government and institutions. So we have to provide a solution which is kind of like you could say Teams or Slack, but without the NSA looking over your shoulder. We have a really really strong focus on the privacy and security. So we have a lot of mechanisms in place in code-wise and in terms of development. So we and for producing this tool, we have many parts. It's mostly a two-tier architecture. We have on one end the backend, and on the other the various clients or front ends. We have the Android client, iOS client, and so on and so forth. And regarding the backend, which is available on GitHub, which is called Wire Server, it's a quite large project. We have roughly 2,000 modules with a bit more than 360,000 lines of code. So big issue we have is that we have many ongoing migrations for years. So, for example, since I have joined a bit less than 1 year ago, we are still migrating from microservices to monolith. We are moving from integration test to unit test, and we have some various approach, which is important to grasp for the next for the next slide. In terms of policy at Wire, it's really pushed by the C-level, including the CTO, for experimenting, for creating proof of concept. I think the AI is pushed not only for the developers but also for the management. I saw many of high-level management producing POC and trying to implement some basic new plugins, which is important for us to see that it's something we can do. We have two policy in order to point the policy in order to keep our software secure and privacy focused. The first one is that you can only use your LLMs on public code or data, which is the case of most of our code, because we are again working on GitHub. And if you can't, for example, if you have to batch process logs and so on and so forth, we are forced to use either anonymized customer data, which is the case for many marketing and sales, or you have to use providers which are not using data for training, or at least saying that they are not using it, which is a bit more restrictive. To understand what is our SDLC, so SDLC stands for Software Development Lifecycle. It is the life cycle of going from the idea. So from us, it is we are writing a RFC, mostly with stakeholders. Which can go from marketing department to front-end developers, for example. We co-create the RFC. Then we have an iteration over the various pull requests. So as everyone knows, I guess, we have the CI which is running. We have also real human code reviews alongside with the Copilot code review, and so we tend to keep focus on that because we want to be able to challenge the architecture of new development, and we iterate on that until the pull request is green. Once it's done, we are doing a release each few weeks, and then we are operating it in production to monitoring the logs and other metrics, and fixing the eventual bug or alert, and so on and so forth. That being said, if I take the regular work I have to do day to day, I would say that maybe something like between 50% to 80% of the code I wrote is adding new endpoints. So my prompts are really simple because I use my a coding agent which is taking basic prompts. So I say, okay, here is what I want to do. Then, in order to avoid confusion and to let the LLM find probably examples which are either outdated or does not fit the current architecture we want to lean forward, I say, okay, just take a look at all these files. Either copy one feature I did like 2 months ago, or just try to integrate everything in these files. It helps to increase the accuracy of the response. And then I have what we currently call the harness, or the guidelines or the loop, which is what are the conditions you will loop until this are met. In case of Power Server, we have already guidelines which were done for humans. Plus, we have some items in our agent.md, which okay, you have to make sure that the pull request compiled, that the lint is green, that you have created a chain log, and so on and so forth. So once I've done that, I just let him generate a plan, which is useful because along the way, the coding agent will always refer to the plan he generated initially and really complete that. It helps to focus the development in the code generation, I should say, and have a clear loop. And generally, after 20 to 30 minutes, because it takes a bit of time to compile it to have the feedback loop complete, I get some result. A quick word on the plan. So the plan is, I try to have comprehensive plan, meaning that it will list the various files it will touch, what more or less it will add, and eventually and possibly the commands he will use in order to verify if it is on the right track or not. On top of that, in order to improve my response time, I did few commands I overuse, meaning that in each part of the SDLC process, I say, okay, for the RFC, I have a / command explore, which tells me, okay, just this morning we were writing a new RFC because we discovered a new bug, and we don't want it to be happening again. So we say, okay, let's scratch a new way to do it was API breakage check, and I say, okay, just let's explore and let's see the impact of doing so. And I had a generated list of endpoints which would be affected. And so it was really helpful to say, okay, it's something we can handle in 1 or 2 weeks, or we could say, okay, it's too big for now. Let's try a first step which should be different. I have the fixed PR, which say, okay, for example, when I had a first review with a lot of various little change, I say, okay, let's take this URL, handle all the small change, and on my side, I will try to fix the bigger one, so I don't get annoyed by the noise of some typo and so on and so forth. I have the fix CI, which is okay. This pull request has a regression. Let's try to do something with the fix. And recently, it didn't work until I think 1 or 2 months at the new models, the fixed rebase, which is really handy when you have very outdated pull requests. And finally, for the deploy, I have more or less the same thing with the fix, except that the fix CI is only looking at the diff of the pull request, while the analyze price try to find some place randomly in the code base. In terms of gains, it's like day and night because we don't I mean, on my side, I saw for example, the RFC process, which is usually long because you have a lot of back and forth between all the stakeholders. While here, it's totally manageable to say, okay, we have a half an hour meeting, so we can just say, okay, let's try to scratch something, have some first estimation roughly, while previously we have to say, okay, let's try to write something, then the backend developer in charge would have a look at the code and write something, so it could spread over days. While here it's much more it's much shorter. Similarly, regarding the draft, of course, the draft is not the end result, but the reactivity between the ID and the crash and the fair pull request, or the reactivity between the code review and the fix are really shorter to a few dozens of minutes. And also finally for deploy, it's not always right, but at least it's a good way to have a rough estimate where is the breaking point. Not necessarily how you would fix it, but it's great to have a first view of what the problem is, where the problem is. I wanted to briefly talk about tools for 2 reasons. The first one is that people are usually focused on code, and this is the first tool I use. And the second thing is that I used to use code, and I was banned from it, so I went back and forth various tools. But before that, let's focus on the side tools I use over my coding agent. Usually, if you look at the literature or the paper regarding LLMs, you said that there is a big trade-off between accuracy on one side, on the other, on the context size. So, as a reminder, context size is roughly the size of the message you are sending to your LLM, which is all it knows in order to take a decision to produce the next character it will send. So usually we tend to say the bigger up to a certain point, the bigger the context is, the more accurate it is, and usually it breaks at a certain point. So in the literature, in the paper, we tend to say, okay, the sweet spot is roughly around 128K to 256. In my day-to-day workflow, I tend to stay well above 100K, usually between 50 and 80, which is for me in Haskell the sweet spot. Otherwise, it tends to have less and less accurate results. So in order to keep the number low, I use two tools. The first one is Snip. For those using code code, you have RTK for Rose Token Killer, which is more or less working the same way, meaning that every time your coding agent executes a function, there is a filter around the result to remove the useless part, the useless for the LLM, meaning all the noise. The issue with RTK is that it's written in Rust and it's not extensible, meaning we don't have the Haskell extension for that. And for example, if you have to run Cabal to build something, you will have all the modules listed one by one, which is totally irrelevant because the only important stuff for the LLM is what is the type error or what are the compilation, the test failure, and so on and so forth. So I have written my own rule set around, which helped me to gain a lot over each compilation. And the other tool I use is Beads. Beads is, I can describe it as the command for agent, which is a really simple task tracking tool. So whenever I have a really huge task, I'll try to chunk it, not only to keep the context low, but also to keep my pull request low, because since we are still having human code reviews, the smaller the pull request is, the faster it will get merged. So I try to have pull request around 100 line of code. So I say, okay, whenever I know that my feature will be to be, I say, okay, let's slice my work into various bits, and after I start a new session for each bit and create as many pull requests as I need in order to get my feature done. Which give me not only a good result for pull requests, but also for long-term work. For example, here it's my Bloodhound work, which is a library I took over a few years ago, which is a wrapper around the OpenSearch Elasticsearch API. So I have a lot to cover, and I can't do it in one session. A quick word on providers. As I said, I started with Anthropic and Sonnet. I did it in August last year, and for some reason, one Monday morning, I restarted my cloud code, and I get banned for absolutely no reason. There is huge risk you have to keep in mind is that you are really at the mercy of your provider, and you can't just rely blindly on it for your day-to-day work. Then after this one, I decided to try with Google Gemini, changing to Gemini CLI, which was because it had been deprecated, a bit less powerful in terms of coding agents. I think at the time, Cloud Code was way ahead. The only way to mitigate the lack of planning was to use conductor, which is a good extension at least. The results were a bit less relevant, a bit less accurate. But sadly, in January, they decided to drastically limit their quota, which means that for day-to-day heavy work, it was not suitable. And after that, since January, I'm using ZAI with GLM. The good thing about this provider is that the quota are basically unlimited. For now, I didn't reach any throttling, even though I sometimes have four coding agents working non-stop. So it's really large in terms of work you can do. There is two drawbacks about this provider. The first one is the high latency, even outside of the peak hours. I saw a lot of latency between each request to the API, and you tend to get degraded relatively rapidly, which is an issue because I rather prefer a mediocre LLM with a steady result rather than a good model with really various level of output in terms of quality, because you can't really mitigate that. Otherwise, you will self-limit yourself, and it won't get you high quality output anyway. In terms of conclusion, I would like to I would like to emphasize something, is that you have to iterate first on your output, because it's not because you have a plan which is good enough you can rework it, of course, or you can just say, okay, my plan was good. I just give me the code and I will push it like this. I systematically do a code review myself before pushing it publicly, so changing stuff manually or not. And the second one is you have to iterate on your setup. For example, on my side, I switch from coding agent to coding agent, but also from provider for provider. And for instance, my next step would be to try to self-host my LLM in order to break a bit the constraint we have regarding privacy and security. So I don't have to be extra careful on that anymore. Yes, that's for me. Thanks for attending to my talk, and I will answer to questions if you have any.
Okay, thank you, Gautier. So while we're waiting to see if anyone asks a question on the chat, I have a quick question for you. So I'm curious, when you're using these tools for review, how do you if one of your colleagues disagrees with the AI review, do you default always to what the colleague says? Is there like how do you navigate that?
So my policy about this is that AI is wrong until proven right. So I tend
Gotcha.
to either align with my colleague or say, okay, let's go further into the analysis. For example, last week we have a discussion because one of my colleagues said, okay, the new architecture should be like that, because, for example, we had a background job. We say, okay, we should have always the user initiating the we should have always the user initiating the job. I say, okay, I'm not sure you're right, so I launched my LLM. So okay, is it possible? And say no, because there is at least one job which is not initiated by one user. So therefore you can't do it like this. So I could have said, okay, let's do it, and then just let the LLM fail. But the thing is, you have two caveats doing this. Either the LLM will try forever to fulfill your spec, and from time to time it just can't. That's something which is a bit bad with the open code, is that there is no looping detection while you have it in Gemini CLI. And the other thing is that it will try to break a bit or completely your model in order to fulfill it, and then you could have like a 2-hour session where he's writing a 100 file and you just can't use it in the end. So
Right.
yeah.
Yeah, fair enough. No, I think that policy is sensible, and that makes sense. And it's not that people can never be wrong, but you got to figure out how to navigate it as well, right?
Yeah.
But yeah, that makes sense to me. Okay. Doesn't seem like there were any questions in chat. Chat seems pretty quiet. So thank you, Gautier, again. Thank you for that.
Thanks.
And I didn't know a lot about Wire, so I also learned, I also learned about that as well. So I appreciate it. Thank you so much. So we're going to shift over to our next speaker, which is Christian. Let me set that up on StreamYard. Thank you again, Gautier.
Thanks.
And we're going to go here. And there's Christian. Hello, Christian. And let's get Christian.
Hello, everyone.
Screen up here. So Christian's going to talk to us about Tricorder, and this is a tool for working with Gen AI. And Christian, I'm going to back out, and you take it away from here.
All right. If you guys cannot hear me very well at any point, just give me a shout. Let me start my stopwatch here. All right. So hello, everyone. I'm Christian. I am a software engineer at Twig. And today I will be talking about Tricorder, which is a tool that I built for getting simple, fast, and focused feedback when working on Haskell programs, right? With or without LLMs. I work on this currently with my colleague, Victor. So thanks, Victor, for helping out. To start off, I would like to talk about the coding loop, right? Because this is the essence of developing software. We all do it, right? So whenever we're working on a feature, we start by editing the code and then compile those changes. If that compiles, if the Cabal build or whatever command works, we then test the code with Cabal test. If that works, we repeat the loop until we finish the feature that we're working on, right? Each of these steps can fail, right? So we edit a file, we compile it, somehow GHC is not happy, the types don't align. We then go back to editing a file, we compile it again, we test it, hopefully it passes, and then we repeat until we are done. So the manual workflow that I just described is essentially the same as using a different tool like a language server, right? For instance, if you use HLS, you edit a file, and then HLS takes care of compiling it and emitting diagnostics and integrating that into your code editor. Tests are still not part of HLS as far as I know. But then you repeat. So this part of the loop here is really tight, at least, right? You still have to switch to your terminal if you want to run the tests, but it is a bit abstracted. Tools like GHCID and GHCI Watch, which are TUI incremental rebuilders, they sit next to your source files. They watch it for changes. And once they detect a change, they compile the files. They can run tests. You can have hooks, and then you can go back to watching the files, right? This loop has different amounts of friction, right? And friction reduces time that we spend in the flow state. Ideally, we want to just focus on the feature that we're developing, not worry about getting a command correct or waiting for tests or waiting for recompilation. We just want to keep on working on the problem and solving the problem, right? And this friction is exacerbated by real-time collaboration. And when I talk about real-time collaboration, I'm talking about pair and group programming. So if you've done pair programming or group programming, and you had to wait for the code to build, and it took a long time, and you started talking about something else, or you had to run a magical incantation to get something just right, and neither of you knew how it was. How do we deploy this, etc. These sorts of friction become really, really apparent when you're doing pair programming or group programming. And in a way, the way I code with LLMs, at least, it is basically doing pair programming, right? So there is this tight feedback loop, and
Hey, Christian, sorry to interrupt just for a moment. We have some requests for a larger font, if that's possible.
Oh, okay. It is possible. Is that good?
All right. Sorry about the interruption.
All right. No worries. Okay. So LLM agents, in that regard, they are also a sort of pair programming that exacerbates the friction in this code, this coding loop, right? So how do we reduce this friction, right? Specifically, there's this friction when doing real-time collaboration. The ideal loop for this kind of collaboration should be simple. It's not some arcane command or set of commands that you have to remember or document somewhere. It should be fast. Nobody wants to be waiting on the compiler to build your code and test your code. And it should be focused, right? So if you want to look at the output of running the test suite, you should just be able to do that very easily. If you want to focus on the diagnostics instead, you should be able to do that. Okay, so then looking at real-time collaboration from the perspective of working with an agent, we have a few ways to drive this loop, right? So we can just let the agent do it manually, which is sort of the default. So the agent will edit a file. It will then run Cabal build, Cabal test, etc. Maybe sometimes it will explore your code base to see what commands to run. So it just works-ish. But it is time consuming. You're still going to go through a Cabal build, Cabal test every time. And it is wasteful, right? So in two senses. Sometimes you already have a language server or another tool building your code while you work with the agent. So rebuilding it from scratch almost every time can be very wasteful. And the second way in that it's wasteful is that the output of Cabal build, Cabal test is very verbose, right? So the agent has to either filter it or we fill up the context window very quickly. A second way to drive this loop is to let the agent hook directly into the language server, which is also somewhat simple because some agents and harnesses support it, but it is not focused, right? The language server protocol was designed for editor integration. So it's JSON-based, it's very verbose, and it fills up the context window very, very quickly. So either it degrades the quality of the conversations, or you have to clear it or compact it, which is also a sort of friction, right? And the third way that I investigated for driving this loop is the incremental TUI rebuilders, right? So such as GHCID, GHCI Watch, they provide really fast incremental recompilation. So if you change a file, it will only rebuild exactly what is needed. So if you touch a dependency of a file, you will propagate that. It is a simple conceptual model. It's something that watches your file system for changes to your source code. If it detects a change, it triggers that incremental recompilation. But exposing this information to agents is somewhat difficult, right? My answer to this is Tricorder, which fits in the third category. It's a TUI, an incremental TUI rebuilder. So I would like to talk about that, right? How that works. And I will compare it to JCID, which is an existing tool that does something similar, and to show why I decided to build it and not change JCID, etc. Okay, so if you're not familiar with an incremental rebuilder, it looks like this. And sorry, I think that was a bit too fast, but everything I ran was Tricorder UI, right? So the incantation on the top here. The UI shows us that it loaded 140 modules. The initial loading took 8.9 seconds, and everything is good, right? It auto-discovered 2 test suits and ran the tests, around 500 tests here, which took around 2 seconds to run. And this is a nice overview of the state of the project, right? So if we contrast that to JCID, the incantation changes depending on whether you have multiple packages in your project or not. Let's copy paste this here. It is very, very similar, right? Once this finishes loading here, we're going to be dropped into a screen that looks kind of like this, but that has no tests by default, right? So, but there is a way to add tests. But just to drive the point home about incremental rebuilders, if we touch a file to simulate something changing in the code base here, we expect to see the rebuilders rebuild the parts of the project that were changed, right? And in the case of Tricorder, we can also see that it's running the tests, which is taking a bit longer because I'm streaming. Usually it's a bit faster. Okay, so how do we run the tests with JCID, right? We can pass the test flag here when calling the JC from the terminal. But there's a caveat. It only works for a single test suit. So this is already some friction, right? We have to remember or not run the tests if our project has multiple packages. All right, but assuming we did, we would also get the output of the tests, which I think in JCID's case, it's the entirety of the test output. So it's also pretty verbose here on the screen. Okay, so we continue working on our project, and I apologize here, but the font is being bigger, is gonna hide some of the slides. But let's continue working on the project, and we add some dependencies, right? So we change a Cabal file, for instance, and we can simulate that by touching a Cabal file in the repository. So Tricorder will then restart the daemon, and once it finishes restarting, it will have those dependencies loaded automatically, right? So it's one less thing you have to think about. Every time you update your dependencies or touch a Cabal file, the tool will self-heal, so to speak, or self-update. So we can also do this, achieve something similar with JCID, but we have to either pass in one flag per Cabal file or use a glob, but I couldn't make the glob work. Okay, so now we have this information here into an LLM, right? How do we feed this? And I'm going to close JCID here now. How do we feed this this info to an LLM? Because hopefully we are able to just dump whatever we want here to the LLM and provide the same context we are seeing. With Tricorder, we can just the LLM can just issue the Tricorder status command, optionally with the wait flag to wait for the cycle to finish, for the loop to finish. But with GHCID, we have to output this summary into a file, and we have to remember to clear the file, not to append to it. Otherwise, it's going to get larger and larger. And then the agent can read it with a cat. And in comparison, Tricorder, we can just ask for the status. It's not going to rebuild anything. It's just going to get the status that is already known. And it's a summary, right? So it's compact. It's designed to preserve context. There is another gotcha other than the verbosity here, is that this workflow here with GHCID is unreliable, right? So imagine that the agent changed the file and then checked the status file with cat before GHCID was done rebuilding and outputting the diagnostics and the findings to that status file. The agent will then see stale output and maybe will incorrectly assume that everything is okay, right? Even though it might not be. And this is a failure mode that I encountered enough that it became a big source of friction. Like I think perhaps the biggest source of friction when trying to run things this way. Let me just try to, okay. So just using GHCID or GHCI Watch with LLMs is leaky because we have to know about all these flags for Cabal, etc. It's brittle because we have to maintain a set of flags for watching Cabal files. Invoking the tests like this doesn't really work with multiple packages. And it's unreliable because it might see stale data, right? And this is not even scratching the surface of the problems we found and we had to work around when writing Tricorder when it comes to Cabal and GHCI, right? They were not designed to support this kind of tool. So GHCID and GHCI were not designed for this use case, and I'm not bashing on them. They were designed with a different kind of use case in mind. On top of that, GHCI Watch is now in maintenance mode. So I did consider making the changes and upstreaming them to GHCID, but to get from this incantation to this format here would essentially be a giant PR or a set of PRs, which would mean a lot of work for me, a lot of work for the maintainers, for a use case that was essentially building a different tool on top of GCAD, right? Okay, so at this point, I think it's kind of, at least in my mind, it was clear that the Tricorder loop was the way to go for me. So let's see how it fares against the goals I had for the loop, right? It should be simple. So one invocation, Tricorder UI, should get us a nice overview of the project. It should work for any Cabal-based projects out of the box within reason, right? So we support a set of GHC versions. And if your project has an unusual setup, it's also, I won't guarantee anything, but that is the goal. So if it doesn't work, it is a bug, you can file that. We aim to encapsulate the implementation details and gotchas from using Cabal and GHCI to drive this loop, as we saw. And we aim to have same but configurable defaults, right? So one of the early feedback that I got from people is that they didn't want to run the tests on every loop because some code bases can be quite, some test suite can be quite long, right? So you don't want to sit there waiting forever. So we have a way to configure Tricorder, right? So I think running the tests should be fast, and I would like to have them be run on every reload. But I understand if you want to adapt that. So it is possible to do so with test targets, for instance. We can limit the amount of or which test suits we want to run. For instance, here I'm only saying run the test affiliate test test suit. So now we only have one, or you can pass in the empty list, which means that we will only build the project, but will not run any tests. Okay. You can there are different knobs you can turn here. You can also specify exactly the command that you want to run. Like for instance, if you want to hack on GHC, you can do so by using something like this, and it's going to give you a level of configuration that is very nice. Okay, so configurable defaults. The second part was suppose that it's was the point that it should be fast feedback, right? So it only recompiles what needs to be recompiled. It runs in the background and is shared by multiple consumers. So if we open a second instance of the UI here, and we touch a file to simulate a change, we can see that they both display the exact same output because it's based on the same state, right? Like they are not rebuilding anything twice. It's just happening once, and we're attaching a new client to a shared backend. And to achieve this speed, we also want the loop to be interruptible, right? So imagine we touch the file and we are running the tests, and then another edit happens. We don't want to wait until the tests are finished before we actually start the next iteration, right? And that also, if we have a client that is currently waiting for the results, and we try to touch a file, it will wait, right? It will not start a new loop until the customer that wants that information, that is waiting for that information, gets it back. So that avoids stale data, right? This was the way that I implemented that. Should be focused, right? It should surface the required information at the right time. We can look at how that works by introducing a test failure, a deliberate test failure. So let's say I changed the expectation here from 18 to 19. We see here that the tests will, the summary will show that we have one test failure, but nothing else, right? If we want to see what that test failure was about and get more information on that, we can then move to a different view here, which is the failed tests view, and we see exactly what test failed, what the expected value was, what the actual value is, and the agent then has exactly the same information, right? So it checks the status, sees that the tests, one of the tests failed, and then it can use the test results filtering by failed to get essentially the same information here. Okay, so this in the right format for the right consumer, either the TUI for us humans or the CLI for the agent. Okay, so this is a little overview. We run a Tricorder daemon, and the TUI and the CLI both talk to it via a socket. And that's basically what we've been talking about, not much to it. If there are diagnostics, let me expand this a little bit. We see here that in this example, we have three diagnostics, right? They are indexed by a number, and the agent can see exactly what failed, which file was the problem, what line number it was, and a header for the error. But if it needs more information about it, we have a command that it's overflowing of the screen, but it shows the entire error message here. So the agent can expand it using that index, right? It works for tests as well, like I demonstrated before. You can see just the test that failed. And the last bit of the CLI that we haven't talked about is the Tricorder source command, right? So when we are working through a problem and the API of a given dependency or a library that we use is unclear, instead of hallucinating the API, the agent is given this Tricorder source command, which they can then run with a module name to get exactly the actual source code for that particular function. So if we run this here, we can get exactly the get standard out function from the typed process package, right? We can also omit the function and get the entire module, which is really nice, and it's a way to aid the loop and to keep the loop in the flow. This is all provided to the agent as a skill, right? We have a file in the repository, and we provide a skill for Claude that can also be easily adapted to any other LLM providers. And this file just lists all the commands. It has examples of the expected output, how to wait, how to expand a certain diagnostic. Basically, this presentation that I'm giving right now, but in a condensed way for agents, right? So like I said, it's Claude specific at the moment, but it's a one prompt conversion, and I've seen people use it with Codex already, so it works really well there as well. And I think I can try to give a little demonstration here. If I start a Claude session, hopefully this will work as expected, but I can load the Tricorder skill and ask fix the tests, please, and watch what happens, right? So it looked at the git diff. It ran the Tricorder status wait. It says the build is clean, but one test fails. Let me look at the failure in the test file. Okay, the test is inconsistent. It suggested a fix here. We can say yes. It will then run the Tricorder test results wait failed. So it's waiting until the build finishes, and it only wants the tests that failed. It says all passed, all good, fixed, all passed, all tests passed now. So that is usually how it goes with Tricorder, right? So you just load the skill, and the agent can use it to query the state of the code base. Okay, so there are still a couple of rough edges, right? Adding and removing modules on the fly is currently a bit broken. It doesn't blow the whole thing up, but tests don't work anymore. And this is a limitation that will only be fixed in JHC 9.14. But once that's landed, Tricorder is already ready to support that. Plugin loading also doesn't really work at the moment. And at ZuriHack, I had someone try Tricorder to hack on a plugin. And since I was there, I decided to hack on this, and I actually fixed JHC to enable to support this in JHCI now. So in JHC 10, we will have it will be possible to hack on plugins. And another pain point is that it's a bit heavy to install. This is on us. The dependencies currently pulled in OpenTelemetry, etc. So if you want to try that, it's just going to take a while to compile, to build the first time, but that's it. We have some other features in mind, evaluation comments, which if you're familiar with them from JHCID and JHCI Watch, you can add a magic comment to the source code and then have it show up in the TUI, which with agents is probably going to be very nice. And some other things which are currently not showing. Let me see if I can, just for this here. Okay. We have turbo mode, which will not build the test suits every time. It will just keep a long running session. And then running the tests is essentially almost as fast as the incremental recompilation. But this is going to cost a lot more memory, so it's going to be optional. We might expose some hooks so people can run some custom codes at different points of this loop. We want to add a tricorder browse function that display functions and types exported by a module, and a tricorder search functionality that allows us to then search using signatures, kind of like Google, how Google works. Maybe I'll integrate it using Google. And if you have any ideas, you can please let us know. And it's on Hackage, so you can try it, Cabal install Tricorder, or if you have Nix, you can use this command here, which is also in the repository. If you just want to copy paste it, this will drop you in hopefully this TUI here, right? Yep. So this was Tricorder. Any questions?
All right, thank you, Christian. We have a few questions actually. So one question from from another speaker was the tricorder implemented specifically with LLM usage in mind, or was AI friendliness a side effect of like a more general design?
It was the ideas came from me trying to use LLMs as a sparring partner, right? So as a pair programming in a pair programming session, so to speak. But it works well with real-time collaboration, right? So like I said here, in real-time collaboration, friction becomes a thing, and I wanted to reduce it in both of these scenarios, right?
Right.
And Tricorder works for both.
Fair enough. Yeah. Thank you. Yeah.
Yeah. It also works as a replacement for JHCID or JHCI Watch, right? It's you don't need to do real-time collaboration to use this.
Right. And there was another question from the YouTube chat, which was about Nix integration and what it kind of knows about Nix things. If
it knows nothing about Nix.
Okay.
Nix. We only use Nix to develop it, right? And I use it with Direnv, which means that if I start the coding assistant in a shell that has Direnv, or so the Nix development shell enabled, the agent will also have access to those tools, right? So if I add Tricorder to my Nix shell, the Claude will also have access to Tricorder.
Right, but the tool itself doesn't know about Nix things. Gotcha.
It has nothing to do with Nix. No, it's Haskell. Gotcha. It's implemented in Haskell.
Gotcha. Okay. Well, thank you so much, Christian. We appreciate it, and telling us about Tricorder.
Thank you.
Let's get the next speaker set up. And we have Lorenzo joining us. So, Lorenzo, I'll let you take it away. Thank you for speaking to us.
Okay, hello. My name is Lorenzo. My talk would be about an experiment that I did with AI, and then I'll compare this with with how we use AI at work, and hopefully the result will provide some insights. But actually, I need to maybe warn you that there are more open questions than actually answers. Okay, my job is So I'm a software engineer at Scribe, a European legal tech company, and it's a highly regulated domain. So electronic signatures, authentication, contracts. We work with a lot of third-party APIs, which are generally poorly specified. And so we need to work by trial and error most of the time, because the documentation doesn't always match the actual behavior of the APIs. Also, we are subject to various standards and like EU regulations, and we are subject to external code reviews for compliance reasons. So these are all quite strong constraints. So the LLM policy at Scribe is full ownership. The author of every PR or any change is accountable for everything that they do, and during code review, the author must be able to defend every choice, and they must understand every implementation detail of what they do. But I also need to say that the company, so the attitude at Scribe is quite open. So the policy is not set in stone. So it may change in the future. Also, using LLMs is an individual choice. Usage is encouraged but not mandated. And in particular, in my team, some engineers use them, some don't. And AI attribution is not common. So in practice, we don't let, at least in my team, we don't let Claude do the commits. So whether a PR was AI generated or written manually is not disclosed, basically. So my impressions at Scribe are that LLMs help a lot with things that have to do with code quality. So code reviews, for example, I personally run Claude or Gemini on PRs in addition to my own manual review. They are very helpful to debug complex problems, for like fixing or catching bugs, also for finding patterns in metrics, etc. We've used LLMs successfully with memory leaks, for example, and similar tasks. Also for understanding programs, so also understanding and navigating, so finding where a particular logic lives in the code base, for example. Where LLMs didn't help much is with code generation and with general development speed. So in my personal experience, it wasn't, since we introduced LLMs at work, the development speed didn't increase, at least not like in a visible manner. And I think the reasons are quite obvious, because if you need to know every implementation detail about a PR, you need to read all the code, maybe manually adjust the parts that you don't like, that don't like feel like your own style. So you end up spending a lot of time. And also there is a cognitive like bottleneck, because we still need to understand what everybody is doing, and have like a solid and detailed understanding of the code. So overall, quality went up, bugs went down, speed is roughly the same, and comprehension is the bottleneck. So now we come to the second part of the talk. But first of all, I want to point out that the policy at work is a very reasonable one. I'd probably have introduced a similar policy if I was the CTO, but still there is a question: is a different approach possible? And now we come to the second part. So this is my personal project. So if you're not familiar with constraint handling rules, it's a rule-based programming language. It's quite old. It's a rule engine, which is generally compiled to a host language, usually Prolog, but it can also target procedural languages. It requires a runtime with logical variables, unification, etc. And it's really an academic project. So there are a lot of papers about it. The implementations for Prolog are more or less maintained in the sense that they're not actively maintained, but the Prolog compiler, the interpreters are maintained. And there is no maintained compiler for procedural languages. So all the compilers for Java, C, etc., they are all basically dead. After the PhD is over or the paper is written, there is no real maintenance. So there is a paper that specifies how to compile CHR to imperative host languages, and it's a very detailed paper. It specifies the algorithm in a very detailed and precise way. So a couple of years ago, I had the idea to try to implement the paper, and there was no AI, at least not in the current form. It wasn't really usable for coding, so I did it manually. The idea was to implement CHR plus a couple of additions that are mine. So instead of compiling directly to, for example, Scheme or JavaScript, the idea is to compile to an abstract VM, and then from there compile to different backends. And also, by doing this, the compiler would be extensible with more backends, like user extensible. So the problem is, months later, I had an OS issue, and I lost like 2 or 3 months of work because I hadn't pushed the work upstream, and I gave up because it was a lot of work, and I thought that I wouldn't be able to start again. So quick retrospective on the first attempt without AI, I found, so these are the only 3 things that I managed to implement in like 5 or 6 months. So the VM was quite hard to implement for me. So conceptually, it is quite simple. It's a simple idea, but for some reason, I kept mixing up the meta level with the object level. And yeah, I struggled a little bit, and it took me some time. Also, the rule compilation, it is quite a mechanical job. There is a paper describing it in detail, but still it's quite hard to get it right because there are a lot of details. Unification was easier. It's a known problem, but still it's an error-prone algorithm. So it took me a couple of iterations to get it right. And that's all I was able to implement. Now, basically at the beginning of this year, or maybe it was like in March, I don't remember exactly, I decided to give it another try with AI. So it initially started as a joke with a friend. I didn't think that this would work, to be honest. So I started re-implementing the same idea, but entirely with LLMs and in full agentic mode this time. So I don't review the code line by line. That's the difference with what what we do, for example, at work. And the development pace is much faster because I don't review all the code. This is the repo. And the result is a great success so far. So after about 4 months, the Haskell and Scheme backends are complete. There are like the specs themselves have been extended with new features. So now there are functions that allow you to like abstract over the different backend. Say you want to implement a function that works on lists. You don't have to, like, you can implement a generic function in my language, YCHR, so that you don't have to implement it separately in each backend. And it's been tested again, various edge cases from the academic literature. It also has some like bootstrapping. So the type checker is implemented in itself. And yeah, I forgot to mention that there is also a type system now. And I wasn't able to find any major bugs so far, so it works quite well. And now I have a bunch of questions. So which parts were easy, which parts were harder? Why was it overall so smooth? Is it because like the domain is AI friendly? Is it because the process, the methodology is AI friendly? And is there any actionable lesson that we can learn from this? So the initial idea of the talk was to try to like draw some conclusions from this experiment. So I had some like quadrants about like where AI shines, where a human shines, etc. But upon reflection, I gave up on conclusions, and now like I realized that it's just too early to draw conclusions. I think AI is a new phenomenon, so I'll just explain what I did, and basically I leave some open questions. So some features, some parts of this project were incredibly easy for AI, and basically the LLM got them right on the first try without any bugs, without any need for iteration on the implementation. So surprisingly enough, the VM was very easy. I thought, because it was difficult for me, I thought that AI would get confused, but it didn't. Rule compilation was straightforward. It just had to follow the specs from the paper. Unification, parsing, and also like the features that I needed for the algorithms that I needed for functions were incredibly quick and easy to implement for AI. But in hindsight, it was quite predictable, because these are standard algorithms. So yeah, it makes sense. But I have to say I was surprised. I didn't expect it before this experiment. The parts that took more time are the parts that basically are my additions to CHR. So the module system, name disambiguation. This is because I decided, for some reasons that are off topic now, to share this, to have like functions, data constructors, and constraints share the same namespace. They're all like lowercase, and this makes name disambiguation a little bit harder. So the AI got confused a couple of times. Also, the interactive interpreter was somehow problematic simply because it requires some duplication between with the rest of the code, and sometimes the AI forgot to update the REPL when it modified some other parts, like the command line, for example, interface, etc. And the command line interface was also a little bit hard to get right because of some subtle issues. But these are all my additions. So there are no papers, and so this part cannot be in the training data. So maybe this can be a tentative explanation of why it was slightly harder. So how did I start working on this? I uploaded the paper to Claude AI. So I started in the chat. I had a brainstorming session to make sure that everything made sense, to get also some feedback on the idea. Then once the idea was a little bit more concrete, I moved to Claude Code. I had a long interactive session where I explained the project in detail, and I gave the specific prompt to ask questions until everything was crystal clear. So it took quite a long time, but the result was a file called project MD. So the file is versioned and it's still there. Now it's a little bit bigger. Maybe I can show it. So this is the file. It contains an architecture diagram of the different phases, and then the different parts of the compiler, the abstract VM, all the data type of the VM, and etc. etc. So it's quite a detailed specification. Then I open another Claude Code session, and starting from Project MD, I started giving tasks. I try to split the work in small tasks so that it became more manageable. And then basically that's what I still do. I start brainstorming in the chat interface, so in the web interface, when I have new ideas, for example, when I added the type system or functions, etc. Then I move to Claude Code. I let Claude generate new spec files. For example, you can see there is a spec file for the type system. This was the result. This is written by Claude, but it's the result of a very long interactive session. Then I versioned the spec file, and then I actually do the implementation from the specs, plus my prompts for the specific task. And from time to time, like once every 2 weeks or a month, I ask Claude to make sure that the implementation is consistent with the specs. Okay, now let's come to an important topic, something that we love as Haskellers. So did I use the types? Did I make use of the types? So Haskell is great because when the types are specification, and when something goes wrong, you get some nice error messages like this one, which help you fix the problem. Well, yes, in theory this is the case, but in my experience, by default, LLMs tend to use very anonymous, very simple and mostly anonymous types. So int, string, tuples, and they use error a lot. So when instead of encoding invariants in the types, they use basically runtime errors. So I introduced a style guide. It's versioned in the repository, and I specified that I want it to use named unique data types, that is new types, records, etc., and also to make invalid states unrepresentable. So encode invariants in the code, in the types, sorry. And there is also other, like I also added more rules, and this was really a game changer. So when I introduced this, quality went up considerably, and it unlocked a new kind of pattern where basically I review mostly the types, and I don't read the implementation anymore. I mean, I do read it from time to time just out of curiosity, but it's not my ordinary way of working on this project. And so far it's worked incredibly well because like the types act as guardrails for the implementation. Also so I took a controversial decision which helped with this like pattern I'm talking about. So I don't use polymorphism. So if you know like the trees that grow pattern that is used in GHC, where you have a type parameter and type families to like reuse the same type definition for different compiler phases. I don't do that. I have a distinct data type for each compiler phase. So the same like module or program is represented slightly different in each phase. There is a lot of code duplication, but the advantage is that definitions are more readable and the invariants can be encoded more precisely because defining new types and adding more subtle differences between the different phases is easier compared to trees that grow. I also have an instruction in my agent configuration file to run an independent review after every modification. Agents tend to forget this, but I remind them every time, and it works quite well. It catches issues almost on every modification, even though it's mostly minor issues, but not always. I have a lot of tests, more tests that I can more tests than I have on my like handwritten projects, as you can imagine. And this is another technique that helped me a lot. So I call it agent-driven QA. Basically, it's AI-driven QA sessions where I instruct the agent to read the specs, read the documentation, and check it against the actual program. It's mostly black box testing. So it doesn't actually read the code. It just tests the specs. So it's a very, very effective technique. It catches bugs and also gaps in the documentation. We can have a look. For example, I have this bugs file where like where agents write the bugs that they find. Yeah, this is the kind of report that they write. These are mostly minor things. And also, thanks to this, this was very effective also to expand the documentation, because every time I found like the agent found a gap, I asked it to include it in the specs or in the documentation. Okay, so a quick recap on the techniques, like the methodology that I used for this project. So detailed specifications via interactive chat sessions, restrictive types, and independent AI-based verification, that is reviews and QA testing, QA agent-based QA. Now I have a bunch of open questions. So first of all, is this way of working a good idea? Because it worked well in this particular case. I have no idea whether it would work for other projects. And also, it requires you to give up understanding the code, or at least, I can still read it and understand it, but it's a lot of code, and yeah, basically, it's really a completely different way of working. Another question is whether the industry will move towards this approach. I know that some companies do it, and I'm not sure about the results. And if this is a good technique, can we apply these techniques to other contexts? For example, Scribe, the company where I work, because, for example, at Scribe we tend to have unreliable specs, as I said, lots of trial and error. We have untestable code, which depends on maybe real identities, like you need a real ID card to identify in some cases, or code that may depend on user devices, etc. So this is not easily testable exhaustively. And we have non-technical constraints, so compliance. Like there are things that we need to do in a certain way, and we need to check in the code that they are done in a certain way because of some compliance reason, legal reason. So this technique can be incompatible with this approach. Also, I want to repeat that this is just one experience report, a single data point. That AI in general is like kind of a moving target. So it's very hard to draw conclusions or to it feels a little bit early in general, and there are no best practices yet. It seems that everybody is experimenting their own way. If I have 2 minutes, I want to just mention 2 things that I discovered working with AI. So the first thing is don't fight AI, don't fight the agents. If you see that this session is not working, it's making mistakes, it's getting confused, just clear the session and start from scratch. Whether it is like a coding session or an interactive discussion, I feel that, yeah, it's often better to start again and try maybe a slightly different prompt, or just there is a random element in LLMs, so sometimes it just doesn't get it, so you need to try again. Second tip is that you need to inspect the style, because powerful models in particular are very good fable tellers. So they are able to make you believe that they are doing the right thing by using grandiose language and complex language. So when you feel that you don't understand what they are saying, and you feel that you are too stupid, it can be a sign that the agent is hallucinating. And one technique that I generally use in this case is simplifying the language considerably, asking very simple and straightforward questions. And this generally works to either make the AI realize the mistake or make me realize that in fact, it was right. So in some cases, it works. And that's all. Thank you.
Okay, thank you, Lorenzo. And I'm going to ask you one question as we set up our next speaker, Nathan. So Nathan, I'm going to be adding you to the stage as well. But I'm curious about your agent-driven QA. And what sort of prompt are you giving the agents for them? You know, are you asking them to be like chaos monkeys and just, you know, because you said it was black box. So what are you kind of asking the agents to do for this QA?
Yeah, so there is a file. It's versioned in the repo. It's basically it's quite a long prompt. So I generally tell the agent to read that file for the full methodology,
yeah.
And then I sometimes I ask the agent to focus on a particular part of the project. Sometimes I ask for like a full general session. But yeah, it's specified in the repo.
Gotcha. Okay, great. Yeah, I'll check it out. Thank you so much. All right. Thank you, Lorenzo. And our last speaker for the day is Nathan, who's going to be talking about typed holes in LLMs. And this is, you know, we like typed holes in Haskell. And why not use LLMs to try and generate good fits for those holes? So Nathan, you take it away.
All right. Thank you so much, Jose. And also I'd like to thank the Haskell Foundation for organizing this stream. I work for Twig, and my name is Nathan. I'm a functional engineer. So we're mostly here to talk about LLMs, which I'm going to refer to as a new class of tools, even though they're not super new at this point, mostly because I'm a very late adopter of new technology. But I want to try to, you know, approach them as tools, and just like any other tool, you know, the good questions to ask are things like, what can they do? What are the trade-offs between them and other tools? How can we leverage them with other tools? So for the purpose of the talk, I'm just going to assume that an LLM is a machine that will generate words when you ask it to. It knows about Haskell, and it can do something that looks like reasoning. And as Jose mentioned, we're also going to be talking about typed holes. Haskell developers, we love these. We all know that good type systems can tell you the type of an expression, but a sufficiently sophisticated one can also tell you sort of the reverse question, given a context, what kind of expression belongs in the context. And typed holes are how we ask GHC that question. And so the idea behind this line of questioning was, can we get an LLM to help fill in typed holes? And there's a compiler plugin that does this called a Lemma Holes plugin, which I want to be very clear, I did not write. This is the work of Matthias Gisserarsen. And so everything I talk about from here on is going to be built on top of his work. But a Lemma Holes plugin, it's a GHC plugin, which means it integrates with the type checking phase of the compiler. And essentially, the way it works is GHC will hand off context about a typed hole when it encounters one to the plugin, and then the plugin does something and contributes back diagnostic information that gets presented to the developer with the typed hole stuff. And it's very simple. It's just you add it as a build dependency and let it go. Give it a typed hole, and it will query a model. You have to do a little bit of configuration, but it will query the model and ask for typed hole fit suggestions. So let's look at an example. So here I've got just a little chunk of code. We're defining a new type wrapper over int called user ID with a smart constructor, make user ID. And we'd like to write a function parse user IDs that takes a string and then parses from it a list of user IDs under the assumption that the string has a bunch of numbers separated by spaces. And the way we ask for that suggestion is to put typed hole in the code. And I mentioned that this example is carefully cherry-picked because at the bottom here, you see we did get a valid whole fit that does work. We could debate whether or not it's the best way to solve this problem, but that's kind of irrelevant. I still think it's a little bit miraculous that linear algebra is able to solve this problem at all. But I also had to do quite a bit of tweaking of the prompt and make quite a few requests in order to get this response. So it can work. We'll talk about some ways that it could work better. So the way it works is pretty simple. When GHC encounters a typed hole, it passes off context to the plugin, which assembles context for a prompt to pass to an LLM. Then we take the response from the LLM and go through a parse, rename, check phase to make sure that we only present candidate fits that are valid, at least type valid. And so the idea is that the model is responsible for proposing suggestions, and then we still rely on type checking to ensure that they are valid. So for the last couple of months, I've been hacking a little bit on this plugin, mostly to try to understand more about AI. I have only been using LLMs in earnest for 6 or 7 months. So I wanted to understand more, what they're capable of. So in using it, I decided to add a few quality of life improvements. So for example, by default, the plugin calls the model at every hole, which tends to be slow. It adds a lot of latency to your type checking. And it also precludes normal use of typed holes, which we all love and know. So to solve this, instead of sending every hole to the LLM, we use triggers, which are prefixes that you attach to your typed hole's name, and then only certain prefixes go to a model. And as a bonus, by configuring different prefixes, you can use different models simultaneously. For example, a local model, like from using Olama, or more expensive remote model. Another issue is that the quality of the results that you get out of an LLM can be very dependent on the exact prompt that you use. But by default, the prompt in the plugin is hard-coded. So I moved that to files so that it's much easier to experiment with different prompts. You can also associate different triggers to different templates. In case you want to experiment with how that affects the results that you get. I also added config files. The current plugin is configured using Cabal arguments, which is a little bit painful. And an added bonus of moving that to config files is that we can sort of mix and match different ways to configure backends to query the models, and also different templates and model parameters. And finally, the last big addition was deduplication of whole fit suggestions. So there's the plugin already did a syntactic deduplication, where if the model would present this exact same suggestion more than once, we would throw out all but one, of course. But it would still let through semantic duplicates. So for instance, id and lambda x to x, they represent the same thing. So we'd really not like to have both of them be presented as a suggestion. But at the same time, they're not equally useful. And so there's also a feature that does a little bit of analysis to try to decide which of multiple semantically equivalent expressions is the simplest. And I should mention that when I say semantic equivalence, that's very loose. It's very conservative. So we're not trying to do any kind of like full semantic analysis. It's mostly eta reduction. But you can also see the details of how that works in the debug mode if you want. So more interesting than the exact changes to the plugin were some of the failure modes that I noticed when trying to use it. And when I say failure modes, I don't mean failure modes of the plugin. I mean failure modes of using a large language model to try to find typed whole fit suggestions. So most of the errors fell into one of two buckets. The first is the model would make suggestions that are correct, but that would not pass review. So for example, here, this is a modification of the first example. We've got our user ID type, and now instead of a smart constructor, we're using a parser that first runs the input string through this all is digit check before trying to return a user ID. And surprisingly, I guess it shouldn't be that surprising, but relatively minor changes to the code or to the types can have a big impact on how much difficulty the model has finding valid fits. So for instance, in this case, it doesn't take too many attempts to get some genuinely correct fits. Although these two examples here that I got pretty often with this example in testing are not optimal. For example, the first one calls read, which is unsafe, and it was being used in a way here that would be safe as long as this code never changes, which of course is not, we can't hope for that. And in the second example, this maybe nothing is also correct, but it's really just a very long name for fmap. This could be written in a much simpler way. So the first failure mode is sort of things that are correct, but awkward. And the second failure mode is that type checking will filter the suggestions by the type, but it knows nothing about intent for the most part. So here's another modification of the parsing example, where now it's very difficult to get the model in my testing to produce examples other than trivial ones, which in this case represent errors or empty results or even infinite loops by just having a function call itself. And the big problem here is that the types can only, or they do and they can only encode so much about the intent. So this was my first time really using LLM as a development aid in earnest. And I did learn a lot of things about the process that I thought would be useful to try to carry forward. For one thing, I had never touched the GHC API before this or worked with any plugins. And I have to admit, ChatGPT helped me to get up to speed with what I needed really quickly. I also found that brainstorming with the model was really effective as an associative memory enhancer, where I could spitball or ask it questions, and then it would respond with a response that had threads that would remind me of things that I had known or heard about, and I could follow them further, that I might not have come up with on my own or nearly as quickly. And the model was also, using a model is also really effective for what I call the boring stuff. And an earlier version of this slide listed some things that I thought of as boring, and it occurred to me that they might not be things that everyone thinks is boring. So whatever you think is boring, there's a good chance that you can get some help from a model and make it less of a chore. But of course, there's some things that are not great. or that you have to watch out for when using a model. For one thing, the LLMs tend to think the answer to everything is to write more code, which of course is not always the case. They're also very good at generating nonsense that is plausible, and having an external judge of correctness like a type checker or a theorem prover is very useful. And I kind of think that probably the most effective way to use LLMs moving forward will probably involve them being in conjunction with more formal tools like that. So ostensibly, this project was about looking at this plugin and trying to make improvements so that we can use an LLM to generate hole fits. So I could talk about future work along the lines of trying to integrate it with other tooling, or learning better best practices about how to prompt for good results, or how to fine-tune models to get better results. But I was really more interested in learning more about LLMs as a tool. And the experience of working on this raised some other questions that I thought would probably be more interesting and impactful. I started this talk by saying that LLMs are a tool, and we like to say that it's important to use the right tool for the job. And so I think a question that I don't know the answer to, and I don't know if anyone knows the answer to, is exactly what jobs are LLMs the right tools for? And the best answer that I've been able to come up with for this so far is that they're like calculators for metaphors. And in the sense that they do literally represent sort of language as linear algebra and manipulate them in ways that look like reasoning. And there's a sort of philosophical debate over whether they actually are reasoning, which I think is kind of irrelevant. If we thinking of them as calculators, we don't argue about whether your desk calculator knows what addition means, because it doesn't matter. It is a tool that performs a task. And similarly, I don't think it really matters whether an LLM is doing reasoning or understands what it's doing. It's a calculator. And so from there, I'm curious about what are some good, or what are the best ways to leverage that capability along with formal analysis to make formal analysis the gatekeeper of correctness. Because I can understand very well what a type checker does, or what a theorem proof checker does. It's very difficult to understand exactly what the LLM is doing. But I did think it's interesting that in both cases, best practice involves making what you mean as explicit as you can, or as explicit as possible. In the case of an LLM, though, more explicit meaning is easier for humans to understand than less explicit. While on the other hand, with formal analysis tools, being more explicit tends to make it less understandable for humans. So is there a common language that the two can speak so that we interact with the LLM interacts with formal analysis, and then we can have sort of the best of both worlds, being able to communicate with the tools using a language we understand, and getting the formal guarantees of correctness. So I think of that as trying to use the LLM as a semantic constraint solver, where if you think of writing code itself as a constraint solving problem over language semantics, what you want the code to do, etc., can the LLM sort of be a solver? And I don't know. I think that several speakers today have mentioned the word specification. And I'd like to be able to think of an LLM as solving a constraint over a semantic specification. But I'm not aware of any especially good or effective tools to do that. And that's sort of where I'm interested in going further. And that's all I've got.
All right, thank you, Nathan. A few comments from myself. I'm going to give myself priority here. So one is, if you didn't have to worry about how hard it was for GHC to do, do you think that like comments and more non-code context should be able to go into the type checker plugins?
That's a good question. And actually, I didn't mention this in the slides, but the plugin does bring in Haddock documentation.
Okay.
And it can bring in
Okay.
some other context, which is useful.
Right.
So yeah, the short answer is yes. I think more context,
Yeah.
more context is better.
Right. Fair enough. And I liked your analogy of like, calculator for metaphor. I hadn't heard that before, but I do dig it. But yeah, thank you. So, Nathan's our last speaker of the day, so we can wait another minute in case there are any questions. But otherwise, I just want to say thank you again to all of the speakers. This was a kind of idea we had and tried to put together all in a short amount of time. And so the speakers did a stellar job of creating talks for today and delivering them. I know it's always awkward when you're kind of just speaking at your computer, but you all did really well. But yeah, looks like we have no further questions. So Nathan, thank you again for everything. And for everyone else, we'll be signing off now. And thanks for stopping by. Bye, everyone.